How are you? Today we'll discuss about a concept of combination of springs, and the next we'll discuss about coupled oscillator, and then after a numerical on this combination of springs. Okay, here combination of springs. So the springs are connected in two ways. The first one, the first method, it is series combination of springs. So in this series combination, the end of the first spring is connected to another end of second spring, and of course third, like fourth, and at last a block is connected. Let the mass of block is taken as m, and the first end of the spring is connected to a rigid support. Such combination is called as series combination. Okay, here consider two springs are in series combination. The spring constant of first spring is k1 and second it is k2, and the block it is on horizontal surface which is frictionless surface. Now pull this block M and release it, doing the oscillations from main point. Okay, in this series combination, the extension in the springs are different. Let extension in the first spring it is x1, and extension in the second spring it is x2. Total extension can be written as x is equals to total extension in the system which are connected in series combination. X is equals to x1 plus x2. But already we know the restoring force concept. Restoring force F is equals to minus kx. So from this the extension can be written as x is equals to minus F by k. I am using this equation. So x is nothing but extension can be written as force, and the resultant spring constant in series combination is taken as kx. x1 is nothing but minus f by k1 plus x2, it is nothing but minus f by k2. Of course minus f is cancelled out in all the terms. Then remaining the final equation is 1 by ks is equals to 1 by k1 plus 1 by k2. So this is the resultant equation in series combination. 1 by ks is equals to 1 by k1 plus 1 by k2. Instead of two springs, if three springs are connected, then the resultant it is 1 by ks is equals to 1 by k1 plus 1 by k2, and third spring it is 1 by k3. And the same equation also written as ks is equal to, taking LCM and taking inversion, ks is equals to k1 k2 by k1 plus k2. This is series combination of the springs. Now the second combination, it is parallel combination. Parallel combination of springs. So in this combination, the first ends of the springs connected to one common point. Let the common point is taken as a rigid support, and the other end is connected to a block. Let the mass of block it is taken as m. So such combination is called as parallel combination. Two ends are connected to one common point, and other two ends of springs connected to another common point. Or also like this, the same diagram, right? See, two springs are connected like this. The first spring attached to the block mass M, and the other spring same connected to block as well as other end is connected to rigid support. Such combination also known as parallel combination, and K1 K2 are the spring constants of those two springs, and extension it is same in the parallel combination. If you pull the block and release, the extension developed in those two springs is remains same, no change in the extension in the springs. But in series combinations extensions are different. Restoring force it is constant, but in the parallel combination restoring force are different, but extension developed in the two springs are same. So the total extension F can be written as F1 plus F2, where F1 is a restoring force in the first spring, F2 is a restoring force in the second spring. So for restoring force equation, F is equals to minus Kx, I'm using here minus K, resultant is taken as P is a parallel combination, X is equals to F1 is minus K1x and X2 it is minus K2x. X cancel, minuses cancel, then the resultant spring constant in the parallel combination Kp equal to K1 plus K2. So this is the resultant equation in the parallel combination. In series combination we got 1 by Ks equal to 1 by K1 plus 1 by K2, but whereas in parallel combination Kp equal to K1 plus K2. Okay, see this example. Three springs are connected in the given system. Now identify which springs are in which combination. Just think about it. See here 1 and 2 springs are parallel. The resultant of these 1 and 2 springs and also parallel to the third spring. So simply these three are in parallel combination. Okay, let me give one more question, one more example. Now just identify these four springs are connected in which combination. So try to give the answer in comment box. Okay, now we'll discuss about coupled oscillator. Coupled oscillator. So spring is attached to two blocks of masses M1 as well as M2. So the such system is called as coupled oscillator. Coupled is nothing but two. So two blocks are connected to the spring and spring constant of the spring is taken as K. So if only one block is attached, then the time period already we know T equal to 2 pi root over M by K. This is for one block. If only one block is attached to end of the spring, then this is the time period equation. Now here two blocks are attached. Then in this case, the time period of this coupled oscillator can be written as T equal to 2 pi root over mu by K. What is mu here? We know K is a spring constant, but mu it is known as reduced mass. Reduced mass. So reduced mass mu is equals to M1 M2 by M1 plus M2. So in a place of mu, now you can replace with M1 M2 by M1 plus M2 and solve for the time period for coupled oscillator. Okay, see one of the example problem on combination of the springs. three springs are connected in parallel combination. The spring constant of first two springs are K1 and second it is K2. Okay, you can take K1, K2, K3 also, but I'm calculating very simple method, right? And theta is an angle and mass of block it is M, and these three springs are connected rigid supports. Now I'm calculating what is the time period of the system. Now pull the block and release it. It doing the oscillations. Okay, the extension in the second spring it is taken as Y, and these two springs spring constant it is same. So in these two springs extension is taken as Y dash. So when it is doing the oscillations, I'm redrawing this diagram again, right? Let us say the first K1 spring and this is K2 spring, sorry, K1 again, and this is K2 is the initial state. When it is doing the oscillations, right? So this is the extension, right? This is Y, the extension in the first spring, and this is Y dash in the second as well as third springs Y dash, and this is theta. This is theta means, so it is also is equals to theta. I'm zooming this diagram. This is Y, this is Y dash, and this is theta. So from this diagram, from this triangle, writing the value of cos theta. Cos theta is equals to opposite by, cos theta is equals to adjacent by hypotenuse. So it becomes Y dash by Y. So Y dash is equals to Y cos theta. Now what is the restoring force developed in the two springs? The restoring force, it is in this direction, of course in this direction. The restoring force is nothing but F is equals to Ky. K is a spring constant, it is K1, and Y dash, okay, it is in this direction. So resolving into two components, horizontal as well as the vertical, this is theta. Okay, so this is K1 Y dash sin theta, and this is K1 Y dash cos theta. Same for the second spring also. This is K1 Y dash sin theta, and other it is also K1 Y dash cos theta. The horizontal components are equal and opposite to each other, so cancelled out. The restoring force developed in the first spring it is K2Y. Therefore, the net restoring force can be written as minus Kx. K is the restoring, K is a spring constant. So in the first spring K1 Y dash cos theta, second spring K1 Y dash cos theta, third it is K2Y. So therefore the net can be written as 2 K1 Y dash cos theta plus K2Y. F is equals to, so F is equals to MA equal to, so minus 2 K1 Y dash. What is Y dash? Already we wrote Y cos theta, multiplying again cos theta plus K2Y, that is MA equal to minus of 2K1 Y cos square theta plus K2Y. Y is taken out and M is bring out, then acceleration becomes A equal to minus of 2K1 cos square theta plus K2 by m into y. So the equation is comparing with a equal to minus omega square y, which is SHM equation, a proportional to minus y, or a equal to minus omega square y. In place of omega square, just to compare these two equations, acceleration is same, displacement is y, minus is okay. Now in the place of omega square, equal to 2k1 cos square theta plus k2 by m. Now I am writing omega. Omega is equals to root over 2k1 cos square theta plus k2 by m, but time period 2 pi by t, omega is 2 pi by t, root over 2k1 cos square theta k2 by m. So the time period can be written as t is equal to the time period of the given system, t equal to 2 pi root over m by 2k1 cos square theta plus k2, the resultant time period of the given system. So if it is three different spring constants are given, k1, k2, k3, same method you can apply, but instead of here 2k1 y dash cos theta, you will get third term because three different spring constants. Okay, and try this problem. Three springs are connected like this. Three are identical springs, same spring constant. Let mass of block is m. The angle it is 90 degree and it is 135. And mass of block it is m, and these three are connected to rigid supports. So try to calculate the time period of the system and tell me the answer in the comment box. Okay, thank you, and please subscribe my channel, like, share and subscribe. Thank you all.